Welcome to the latest in our video series on laboratory safety. Today's topic is the trigger grid, hazards to assess. This is the second part of a three-part series regarding managing change in the laboratory. Discovery may be one of the most exciting things about chemistry. We love using chemicals in new ways to create new molecules, and change is the very essence of chemistry. Yet there's an aspect of change that is often overlooked in the lab. The changes we make to our experiments that may impact our safety.
We have a creative solution that can help us recognize the safety impact of process changes. It's called a trigger grid, and it is a method designed to help researchers assess changes to the process, their impact on safety, and define potential hazards. So before you make a change in your experiment, stop. Use a trigger grid first to investigate what that change may really do. Let's take a tour of a trigger grid together. We first start at the General Considerations section of the grid. In this section, you will be asked to consider putting together a peer group to check out your ideas before you proceed. A peer group can help you review the changes you've planned to your experiment, assess the hazards associated with the project change, and, perhaps most importantly, provide additional expertise, experience, and insight. The more complex the process, the more important it is to have a second or third or fourth set of eyes. Your reviewers may identify hazards that were not evident in your project plan. Also, consider inviting environmental health and safety, or EH&S experts to your review. They can add information concerning proper personal protective equipment, chemical handling, and waste disposal. Our next stop on the tour is the General Changes section. Here is where you take the time to think through the changes you want to make to your experiment. Changes like personal protection equipment, or PPE. You may find that what you used previously may no longer be sufficient. Not all glove styles are effective for the hazards of specific tasks. An EH&S expert can help identify the correct PPE that is now needed. New people to the lab or task. New is always a cue to stop and assess. So as you train new people, use your procedure document. Have them follow the document while you show them the task. If they don't see a specific task being done as written, discuss why you are doing it differently from the procedure. New procedures developed. Input and perspective from experts about your new procedure can be invaluable. Ask your coworkers to do a procedure walkthrough with the equipment. This helps you identify and correct potential safety issues up front. And with this input, you are better able to develop a procedure that reflects how people will actually use it. Ergonomic considerations. These need to be addressed as equipment is set up or procedures are developed. Look for tasks that are repetitive, involve standing or awkward positions, or require heavy lifting. Then find ways to incorporate equipment that will reduce repetitive motions like pipetting. And consider the stature of users to minimize reaching, bending, and stretching. Finally, reduce lifting hazards by using lifting aids, requiring additional help, or ordering smaller quantities. Now we move to the Equipment Operating Changes section. For this part of the trigger grid, remember, your experiment is only as successful as the vessels you choose to use. A safe and successful project depends on selecting vessels made of the right materials. How do you figure out what's right? First, think about the compatibility of the vessel with the chemicals it will hold. The last thing you want is a reaction between the chemical and its container that leads to spills, leaks, and other problems. Choose compatible materials. Next, consider the impact pressure will have on the vessel. Glass vessels are generally not used under pressure since they can explode, and metal containers, if not properly relieved, can become bombs if overpressurized. Be sure to consider the maximum potential pressures a vessel material can handle. With that information, you can then choose the proper vessel, design pressure reliefs, and install proper protection in the event of overpressurization. Protective shielding could include netting or tape on vacuum flasks, shields in front of glass vessels, or lab fume hood doors. Don't forget to think of heat and the impact of oven temperatures on your procedure. Consider the chances of personal contact. Is there potential for burns? Labeling, protective shielding, and heat-resistant gloves may be needed. And what about an oven overheating? Could this cause unwanted degradation, exceed flash point, or evaporate solvent? If there are negative consequences to an overheated oven, use a secondary high-temperature shutoff. Will your experiments run unattended? Then you need to take extra precautions. Evaluate worst-case scenarios. If there is potential impact, add monitoring systems that can shut down the process automatically or indicate that there is a problem. And by all means, let any emergency services or similar group available know about your experiment and who to contact if there is a problem. Finally, ventilation is included in this section. This gives you the opportunity to consider the impact of altering a hood or other ventilation device in your procedure. If the airflow is altered in any way, even just turning off a hood, the air balance can be greatly affected, potentially increasing the risk of exposure. Last, but definitely not least, the chemical change section asks you to consider the physical and toxicological properties of materials being used in your procedure and how to minimize their potential hazards. You can find physical properties and toxicological information on Material Safety Data Sheets, or MSDS. Make sure you have an MSDS for every material involved. For inhalation hazards, your project planning should focus on how to minimize the potential for vapors in your breathing zone. Use chemical fume hoods or local ventilation. Then verify that the ventilation works as designed. As for skin or eye contact, you must clearly identify the correct type of gloves and chemical worker goggles to wear if needed. Remember, if there is any splash potential, goggles are the eye protection of choice. For flammable solids, consider all of the potential conditions that could cause the material to ignite. That includes assessing storage, proper handling techniques, and waste management. Your EH&S expert can be a tremendous help in this area. Also, determine worst-case scenarios and document how you will respond if there is a fire. Material reactivity is the final consideration in this section. Use basic thermodynamic properties and calculations and online references such as Bretherick's Handbook of Reactive Chemical Hazards or SciFinder to further evaluate the reactivity of materials.
Change can be good, and if we don't make changes in our processes, we will never improve them. But don't let the excitement of discovering something new overcome your common sense. Excitement, change, and safety do work well together. Put them to good use in your lab work.